Two sessions, which are both on neural network architectures and deep learning. The first talk is going to be given by Abhishek Bansal, and the title is Using Inherent Structures to Design Lean Two-Layer RBMs. Thanks.
Good evening, everyone. I'm Abhishek Bansal from IBM Research, and I'm very glad to present our work on using inherent structures to design lean two-layer RBMs. This is a joint work with Abhinav Anand and Professor Chiranjeev Bhattacharya from Indian Institute of Science, Bangalore. So in this work, we study the representation power of generative neural networks, particularly single-layer and multi-layer deep restricted Boltzmann machines. And using ideas from statistical mechanics, we derive some insights. So deep Boltzmann machines have been used quite extensively in the past. For example, generative modeling of handwritten characters, 3D objects, even multimodal learning, so given an image to generate the corresponding textual tags, and vice versa. However, there is still not much theoretical understanding behind why we need more layers. In fact, previous research has shown that even a single hidden layer RBM is enough to model any distribution on the input vectors, given sufficient number of hidden units. So in light of this, why do we need more layers? So this representation power has been studied in the past in terms of the modes of the input distribution, and we take a similar approach. Some basic notations that we follow. We consider only those RBMs and multi-layer DBMs for which the visible and hidden units take values either 0 or 1. And we denote by RBM nm theta a single layer RBM with n visible units, m hidden units, and model parameters theta. For such an RBM, the joint distribution and the marginal distribution is given by this equation 1, where E is the energy function that has A, B, and W as parameters that constitute theta. So for this work, we set A and B to be 0, but the analysis could be extended to non-zero A and B in a straightforward manner. So we are interested in measuring the representation power for an RBM architecture. Towards that end, we denote the set of all RBMs with n visible units, m hidden units, by architecture boldface RBM nm. And similarly, for a multi-layer DBM with L layers, we denote that by RBM n, m1, m2, up till ml. So for a given distribution P, we define the support set to be those vectors that are given non-zero probability by the distribution, and the modes of P to be the local maxima of that probability distribution. By local maxima, we mean if we change any unit from 0 to 1 or 1 to 0, the probability of that vector decreases. So there is an immediate connection between this support set and modes of P. If the vectors in the support set are at least Hamming distance 2 apart, that is, they differ by at least 2 units, then the modes of the distribution are nothing but the vectors in the support set. So the input distribution that we consider is such that it gives positive probability to k vectors, where k is at least quadratic in n. So there's this very interesting concept that was introduced by Montefort and Morton in 2015 that we shall use, called perfectly deconstructible vectors. So given a visible vector v, we define the operator up of v to be the most likely hidden units vector given v. And similarly, given for a hidden unit vector h, we define down of h to be the most likely visible units vector given H. And we call a vector V perfectly reconstructible if, after performing these two steps in sequence, we get back our original vector. And we denote the set of all perfectly reconstructible vectors by PRV. So it was shown that if the input distribution obeyed these two conditions, then there is an equivalence between the perfectly reconstructible vectors and the modes of marginal distribution, which suggests that these perfectly reconstructible vectors can be thought of as surrogates for modes of this marginal distribution under these conditions. So having defined these quantities, we briefly survey the past work that has been carried out in this direction. LaRue and Bengio in 2008 showed that any distribution with support set size k could be approximated arbitrarily well with an RBM with k plus 1 hidden units. Now, this was a very fundamental result since it gave a strong guarantee of sufficiency condition for an architecture. However, this k, as we see, is at least quadratic in n, and in fact, it could be exponential in n. So, and there have been further refinements to these results, but the number of hidden units required in the worst case remain exponential. So Montefiore and Morton related the representation power of RBMs to the modes of marginal distribution. In particular, they asked this question, what is the smallest m, what is the smallest number of hidden units such that the architecture RBM NM contains a distribution with k modes. And they showed that answering this question in an exact manner was related to the problem of computing covering numbers of n-dimensional hypercubes, which is a known computationally hard problem. So just to check how strict this bound of k plus 1 hidden units is, we conducted simulations. In this graph, we have fixed the value of n, the number of visible units, and on x-axis, we vary the hidden units. On y-axis, we plot the number of modes generated by the corresponding architecture. So this red graph is nothing but a straight line that gives the worst case scenario that an RBM NM architecture, for an RBM NM architecture, the number of modes generated will be m minus 1. On the other hand, we conducted simulations. We generated random weight matrices and counted the number of modes by brute force and averaged our readings. We saw that on average, the number of modes generated is much larger than this bound, which suggests that average modes could also be an important metric to measure the representation power of an RBM. Thus, we assume a Brier on the weight parameters. We assume that the entries are IID, Gaussian, mean zero distributed. And under such a scenario, we ask the question, what is the expected number of modes of the marginal distribution model for an architecture? How does this number change as we increase the number of hidden units? Also, whether there is an efficient two-layer DBM architecture that has the same or more representation power than a large single-layer RBM. So before answering these questions, we briefly discussed the significance of this number, the expected number of modes. It turns out that this number has a very deep and interesting interpretation in the context of statistical mechanics. So RBMs, as we know, are a special case of Boltzmann machines that in turn have originals in this Ising model. So this model does not need an introduction, but just for clarity notation, this model consists of n sites, each site taking value either +1 or -1. And they interact among one another through weight matrix W. And the probability distribution is given by this Boltzmann law, where Z is the partition function and E is the energy. So Stillinger and Weber, way back in '82, studied this energy landscape of spin glass Ising model. And they showed that it exhibited a very interesting structure with multiple local minima, or one-flip stable states, as they called it, which are denoted by these blue valleys. So these one-flip stable states are nothing but the joint modes of this probability distribution. And in fact, they showed that this energy landscape could actually be partitioned into k valleys, or inherent structures, as they called it, each corresponding to one flip stable state. Further, each state mapped to exactly one inherent structure. And given an inherent structure, if we conducted energy descent, we would reach the same one flip stable state. So such formalism is an active area of study. It has been studied in other contexts also. Now, up till now, we have plotted this energy landscape for a particular instance of W. On the other hand, if we consider the Sherrington Kirkpatrick model, In that case, the weight matrix W itself is a random matrix where each entry of the matrix is distributed as per mean zero Gaussian. And for such a model, the anneal complexity is defined as the normalized logarithm of expected number of one-flip stable states, where the expectation is under the prior distribution on W. So motivated by this definition, we define our inherent structure capacity as a normalized logarithm of expected number of perfectly reconstructible vectors. And the equivalence that was shown earlier with the marginal modes allows us to define this in terms of perfectly reconstructible vectors. Further, by definition, we see that the maximum value this capacity could attain is 1. And we show that there is an equivalence between perfectly reconstructible vectors and the one-flip stable states, or the joint modes. So this suggests that the capacity, as we have defined it, is aligned with the annealed complexity that was defined in the context of statistical mechanics. So having defined this capacity, how do we compute it? Previous methods are rooted in statistical mechanics. They adopted sophisticated approximation technique like replica method under large N assumptions. And it's not straightforward to extend these to layered architectures. In contrast, we follow a completely different approach. For a given visible vector with R1s, we compute the most likely hidden units vector up of V. Let's say it has L1s. And then given this H vector, we again compute, reconstruct a visible vector, the most likely visible vector. Then we compute the probability that this reconstructed vector is same as our original vector, which is nothing but the expectation of the indicator variable, indicator random variable, that is 1 if VR is perfectly reconstructible and 0 otherwise. Now, once we have this number, then we can simply sum over all R to get our total number of expected number of perfectly reconstructible vectors by linearity of expectation. So this actually follows from a key observation that this probability of reconstruction depends on R, the number of ones, but it does not depend on the position of ones in that vector. This we can see by symmetry. If the most likely hidden units vector contains L1s, then conditioned on that, one can show that this probability is upper bounded by this expression. And we can show that L is actually a binomial random variable. So we can marginalize over L to get the upper bound on this probability of reconstruction. So here we show the upper bound, but in the paper, we also derive a lower bound on this capacity. There's a very interesting observation that can be seen in this expression. The upper bound on capacity actually does not depend on the absolute values of M and N. Rather, it depends on the ratio between M and N for a single layer RBM. So once we have this expression, we conduct our further analysis. The first analysis that we conduct is what happens if we increase the number of hidden units. So we see that as we increase the number of hidden units to infinity, this capacity actually tapers to a fixed constant, log to 1.5, which is 0.585, which can be seen as much less than 1. And in fact, if we plot the values of the upper bound, we see that this bound is reached for M as low as 20n, which suggests that the expected number of modes for a single layer RBM is upper bounded regardless of the number of hidden units. To further verify this analysis, we conducted simulations. In this graph, we have plotted the upper bound and lower bound that is predicted by our formula, and also the actual simulated value, which we get by enumerating the modes by brute force, by generating the RBMs and averaging our readings. We can see that the green graph is quite close to the bounds that are predicted by our formula. And the actual number of modes also taper as we increase the number of hidden units. So we extend this analysis to 2 layers also. To do that, we use this observation that a 2-layer DBM shares the same bipartite graph structure as a single layer RBM with n plus m2 hidden visible units and m1 hidden units. So instead of computing the modes of this DBM, we simply compute the number of perfectly reconstructible vectors for this equivalent RBM. However, one has to be cautious. In computing these perfectly reconstructible vectors, there will be multiple vectors that share the same V. So we need to discount for that fact. We won't go into too much detail on the exact theorem, but we'll straight away move on to the implications. So we recall that for a single layer RBM, the capacity is upper bounded by this log 2 of 1.5. What happens if we add another layer? It turns out that as soon as we start adding units to layer 2, the single layer limit is breached, and the capacity starts to increase linearly again. With the so this linearly, as in this M2 is the number of hidden units. So it starts to increase linearly with the number of hidden units in the second layer. So before coming out to the last implication, we define this lean RBMs. We call a multi-layer DBM lean if if the hidden units in all layer is at most C of n, where C is much less than n. And this is actually a special case of narrow RBMs, which was introduced by Montefar in 2014. So given these lead RBMs, we ask this question. If we consider a single layer RBM with the omega of n squared hidden units, that is omega of n cubed parameters, cubic number of parameters, can we construct a two-layer DBM that has the same capacity, but with far less number of parameters? It turns out we can, and we construct a two-layer lean DBM that has theta of n squared parameters, but with the same ISC. And this shows that a two-layer DBM can actually match the capacity of a single layer RBM, but with far less parameters. To further validate our result, we also conduct experiments. We randomly draw RBMs, and we generate data from those single layer RBMs. Using that data, we train a two-layer DBM that is predicted by our architecture. And we see that the log likelihood that we get from a two-layer DBM is at least as good as that single layer RBM. So to summarize, we propose ISC as a measure for representation power. We make practical suggestion as to when multi-layering should be considered. And we show that there is the existence of a lean two-layer DBM that matches the ISC of a single large RBM. But having said that, these results are in expected sense. We would further like to show whether a further guarantee can be proven, just like the universal approximation theorem. So thank you. In case you have any questions, you are most invited to our poster number 107. Thank you.
Thank you. If there are any questions, please go to the microphone. So I was wondering whether or not how your claims extend to layers beyond 2 in DBMs.
Yeah, that's an interesting question. So until now, we have extended our result to 2 layers by using the observation that the bipartite graphical architecture. The moment we add another layer, it still remains a bipartite graph, but the completeness, it does not remain a complete bipartite graph. But yes, this is one thing that we want to explore, and we want to extend this to multiple architectures also.
Any other questions? All right, let's thank the speaker again. Great. The next speaker is Hae Byum Lee, and he's going to talk about deep asymmetric multitask feature learning.
Hello, I'm Hae Byum Lee, a graduate student from UNIST. This is joint work with Eun-Oh Yang and my advisor Seong-Ju Hwang from KAIST. First of all, we start by discussing what multitask learning is. Suppose we are given 3 tasks, tiger, horse, and zebra. And each task is to classify an input image into one of 3 animal classes. Then the goal of multitask learning is to exploit the relatedness between multiple tasks by jointly training them. A popular approach to MTL is task-to-task transfer, parameter transfer, where a model parameter for one task is affected by the parameter for other tasks. Or we can share latent representations between the task-specific models, and knowledge is transferred through those representations. GoMTL by Kuma et al. Is one of such examples. And also, with neural networks, we can straightforwardly implement multitask learning because all tasks can share the common network architecture. And aside from such a trivial implementation of multitask learning with deep neural networks, some recent work explored the optimal sharing structure between the tasks. For example, solution network by Ruder et al. And DMTRL by Yang et al. However, the limitation of those proposed MTL models is that they do not consider the different level of difficulties for a given set of tasks. So when there is a significant gap of difficulties between the tasks, negative transfer can occur as learning for the difficult tasks impacts negatively on performance in other tasks through the shared representations. A recently proposed method, AMTL, effectively solves the problem by leveraging asymmetry in the direction of knowledge transfer. AMTL basically assumes a set of disjoint learners, unlike previous examples. And based on that, AMTL tries to reconstruct the model parameters for difficult tasks as a linear combination of model parameters for easy tasks. Here, the direction of the transfer is only from easy to difficult and not in the opposite direction. This asymmetry is the most crucial part in preventing negative transfer in AMTL. And as a result, the model parameters for zebra becomes close to a linear combination of the model parameters for tiger and horse. However, when a group of tasks are only partly related, model parameters may not be accurately reconstructed as a combination of model parameters for other tasks. For example, we could get zebra, which is black and orange, not black and white, as a result of mixing tiger and horse. Therefore, it would be better if we can reconstruct only a part of knowledge in a symmetric way. To overcome the limitation, we propose task-to-feature transfer, not task-to-task transfer. In this figure, we try to extract stripe using the model parameters of easy tasks, such as tiger and horse. And sigma here is a nonlinearity like ReLU, which is needed for the extraction. And we also try to extract the other features in the same way. The nonlinearity needs to be the same as the one used for the features so that the transformation explores the same manifold of the original features. And since we have extracted features with easy tasks, the features are protected from the negative transfers from the difficult tasks. And such way of asymmetric task-to-feature transfer can be implemented with autoencoder, which is sparse and asymmetric. Let's look at one by one with the formula. Given the features, task output logits are generated through sparse combinations, and again, the features are reconstructed from the output logits of easy tasks in the form of autoencoder. And all these components are trained at the same time. And if we rearrange the layers, we can see that the knowledge is actually transferred from easy tasks to difficult ones, like in this figure. Moreover, to better measure the true risk for each task, we let the loss term be a function of the number of training instances, so that the task with a large number of training instances will transfer more. Next, we introduce the experimental setups and results. We first validate the idea with shallow version of our model, which has only one hidden layer. We test it on a synthetic dataset consisting of 12 regression tasks. There are two groups of tasks, easy and difficult. Easy tasks have small level of noise and large number of training instances, and difficult tasks have large level of noise and small number of training instances. And after training, we check how accurate each model reconstructs the true parameters. This figure is reconstructed parameters from AMTL, and these are reconstructed parameters from GoMTL. And we see that GoMTL is a little bit better because this data set has been generated from the common basis. And finally, these are reconstructed parameters from ours, and we see that they are the most accurate. And this figure shows RMSE reduction over single task learning for GoMTL. We see that there are negative transfers for difficult tasks, And also, AMTR suffers from some degree of negative transfer, although not severe as GoMTR. But our model shows significantly less negative transfer than other baselines. And also in AMTR, the size of the inter-task transfer matrix grows quadratically with respect to the number of tasks. But in our model, the size of the matrix is more scalable if the dimensional feature is relatively smaller. And then the training time is reduced as well. Also, AMTR suffers from poor generalization with large number of tasks, but our model can generalize well. Next, we experiment with deep version of our model. Note that our idea can be easily extended to any deep neural networks such as ResNet. Here we introduce the results on two datasets, MNIST imbalanced and AAA. Those datasets are imbalanced across the classes, and our model significantly outperforms other CNN baselines. And more results are available in the main paper. And to see where the performance improvements are coming from, we analyzed the results from the MNIST imbalanced dataset. This figure shows accuracy improvements over the base CNN for each model and the training cross entropies. And as you can see, accuracies are more improved for the tasks with higher training cross entropies, meaning that the difficult tasks have received knowledge from the easy ones. And this inter-task transfer matrix is supporting that argument. There are more transfer from easy to difficult tasks along this upper triangular area. And also, the number 9 receives big transfers from easy numbers, so the accuracy has been much improved. In conclusion, our model effectively prevents negative transfer in multitask learning based on shared representations such as deep neural network. And our model performs asymmetric task-to-feature transfer using a loss-weighted asymmetric autoencoder term, which fits well to deep neural network models. And finally, our asymmetric multitask feature learning also produces better performances and is highly scalable compared to the existing inter-task transfer models such as AMTR. Thank you for listening. So any questions?
Any questions? This method seems to rely on having a relatively clean understanding of the tasks and the boundaries and things like this. Is there any way that you think that your method could be applied in more sort of continuous environments? Where the tasks are not as well separated, defined?
I think in that case, you mean that task is continually spread, or so what is?
Well, if you don't know, for instance, the relative difficulty of different tasks, then it would be hard to. Maybe you would need to automatically determine the asymmetric.
Yeah, right. Yeah, I think that's very interesting, but I'm not quite sure for now. But yeah, that would be interesting. Yeah, I think.
Any questions? All right, let's thank Hei again.
Yeah.
The next speaker is Bin Dong, and he's going to present the paper Beyond Finite Layer Neural Networks, Bridging Deep Architectures and Numerical Differential Equations.
Okay, good afternoon, everyone. This is a joint work with my students, Yiping Lu from Peking University, and my colleagues, Ao Xiao Zhong and Quanzheng Li from Harvard. So I'm an applied mathematician. This is actually my first time presenting in a computer science conference, so I will try to act like a computer scientist. So I don't think I need to convince you, why deep learning works and you know, what are the good applications of it. I'll start with the challenges that well, maybe the list should go, you know, even longer. You may know better than me, but the challenge that as an applied mathematician we're interested in is the theoretical guidance in network designing and also the algorithm design. So I'll mainly focus on that. You know, many applied mathematicians, this is actually how we think. When we look at something and we try to develop rigorous mathematics, you know, trying to at least answer the questions in our head. But then after a while, I look at, I only started looking at deep learning about 2 years ago, which is much later than many of you guys. But then I started to realize maybe this is not the right approach to, you know, we have an obsession of rigorousness, but this may not be the right thing to do at the beginning. Then I read the paper by Alan Turing, which is, I believe it's in the 50s. He said that we should allow engineers to design a machine that works, but the manner of its, you know, function cannot be satisfactorily described by its constructor. So maybe, you know, looking for rigorousness at the beginning is not the right approach. And then our team start to look to find frameworks, because we have hundreds or thousands of different architectures, and some of them are quite similar to each other. And then we start to ask ourselves, you know, whether there are some relations between all of these different architectures. So basically now, our team, as well as many other people, start to look at, you know, deep networks as dynamic system or discrete form of dynamic systems, and training deep networks can be understood as optimal control, which are subjects in applied mathematics. Okay, so let me just give you the first example. Some of you may already know this, that if you look at ResNet, and if you add this delta t, which normally we just take it to be 1, or it's absorbed in the learning of this function f, but it's a Ford-Euler discretization of a non-autonomous dynamic system. Okay, this is simple, and then training will be just optimal control. And there are many people have fully exploited this direction. And when we look at this and we ask some questions, that is, so first of all, is this a lucky shot? Okay, so how common is this relation in deep architectures? And also, you know, if you have this observation, what can we do about it? Can we design, you know, more effective architectures, you know, using numerical differential equations, and would that help? Okay. So first of all, we look at some of the popular networks, and we found that it's very interesting. Well, we know ResNet, ResNext, it's Ford-Euler, temporal discretization, okay? And the PolyNet, it's approximation of backward Euler. You use polynomial to approximate an inverse, even though this is nonlinear, so it's more or less formal, but it's used polynomial to approximate a inverse. Okay, because it's an implicit scheme. And for FractalNet, the architecture resembles Runge-Kutta very much. Okay, and also RevNet is a Ford-Euler, you know, approximating a blocked dynamic, you know, a block system. And there are other examples as well we didn't include in the paper because it's not as precise as these examples. For example, DenseNet, it's a discretization of a fractional order dynamic system. Okay, so if you look at this list, if you know numerical ODEs, and you will realize that, okay, so there are generally two types of method in numerical ODE. The one is the one-step method, the other one is linear multi-step method, and we don't see linear multi-step method. So we just look at the very simple linear two-step method. We call it LM structure, okay, which can be embedded, you can use that, apply that on any ResNet-like network. Okay, so you just simply, at each layer, you just simply need to learn a scalar. And this is pretty much the scheme, and you can easily write down the architecture, okay? And we first tested on CIFAR 10, and we observe, at least at a certain depth, we observe a 50% depth reduction without dropping accuracy. And actually, before we try this is sort of what we expected. So let me tell you why we expected this when we introduced that. If you do, well, in numerical analysis, there is a concept called modified equation, which is very simple. You just do Taylor expansion, and without dropping this term, you just drop the even higher order term, and you sort of see the behavior in the discrete setting of this dynamic system. And if you compare ResNet and LM ResNet, and you will see that this additional weighing factor that allow us to have a dynamic system that has more weight on the second order term. Okay, you don't see that in the ResNet, but you do see that in the LM ResNet. And this does help because in terms of information propagation, having a second order, even though it may be oscillatory, but it propagates information much, much faster. So that's why we observe a similar accuracy at a with a shallower network. And of course, these scalars are actually trained. And if you look at how the scalar Kn trained, well, most of them actually falls under the value 0, which gives more weight in the second order term than the first one. Okay, so well, this is actually our original motivation of looking at this. This is second order linear multi-step type of network, and it's based on some of our earlier. Well, this is mathematical, more applied math work, and also some work by Candace and also by Michael Jordan. Okay, and on CIFAR 100, we observed something similar. Okay, and with the number of layer reduced, and while we're keeping accuracy, and also we observed something similar on ImageNet. Okay, and we didn't go further because we don't have that many GPUs, so this is as much as we can do. Okay, and during training, there are a lot of tricks. For example, stochastic training, and it's very natural to ask. Okay, so with stochastic training, whether you're actually looking at a stochastic control problem, and the architecture and the network is a stochastic differential equation, and we look at shake and also stochastic depth, and you can identify them as a stochastic differential equation. And it's very interesting when you try to prove that it does converge weakly to the stochastic differential equation. And for stochastic depth, the dropping probability, well, in their paper, they empirically show that it has to converge to 0.5, and in our proof, you can see that naturally this dropping probability has to go to 0.5. Otherwise, you will not have a weak convergence to a stochastic differential equation. Okay, so now with this stochastic control point of view, we can use the same linear multi-step structure to discretize it, and you can use either Gaussian or Bernoulli at applying it on the blocks. And what you can see is that, well, we can achieve comparable accuracy with Huang's previous results, but at only 110 layers, while they're looking at over 1,000 layers. Okay. So basically, I like to quickly summarize that we're trying to bridge numerical differential equations with deep neural networks, and of course, this is not for general deep neural networks. It's typical for deep networks that with bypasses, and there are other type of deep networks like UNet, and well, I have a wavelet background. I think they resemble wavelets or other harmonic analysis tools very much. So maybe you can analyze them, those networks, not using optimal control, but use harmonic analysis or approximation theory. Okay, and also you can bridge stochastic differential equations with stochastic training, and you observe for certain networks, you can observe reduction of parameters of 40 to up to 90%, and you can sort of explain the reduction in terms of information propagation. You use the notion called the modified equations from numerical analysis. And if you're interested in, because I only have 10 minutes, if you're interested in details, our poster is going to be at 127. So that's my talk. Thank you.
Is there any question? Do you have a question? Yes, go ahead.
I was wondering if the connection to PDEs reveals any insights. For instance, the Euler method is not a very good method, but somehow ResNets are good. So yeah, can you comment?
Euler is not good. I don't think I agree with that. For some cases, maybe not. Yeah, stability. If you think of stability, you have a very stiff problem. Then it is not. Well. If you do not go into crazy depth, you may not observe that instability. That's a very hard question to answer. I think for forward Euler, for a lot of PDEs, we try to discretize using forward Euler at the beginning, and you do observe some good behavior. And then If your problem gets tougher and tougher, we look at other different temporal discretization, and we look at the stability. I think maybe this is only my guess, is that well, at this stage we observe the effectiveness of ResNet, but maybe after 2 or 3 years we look at other different temporal discretizations.
So are there any fine scale sort of testable predictions that your framework makes? So because it's being connected to this information flow with this modified equation perspective, is there something we can go probe in these ResNets, that some observable that we should go look for, and if we find it, yes, it confirms your theory?
Well, it's okay. So nothing. So first of all, let me tell you the drawbacks of the work. I don't see a lot of people talk drawbacks of this approach. Well, there are a lot of fine structures in deep networks that we cannot explain perfectly using dynamic system. For example, if you have pooling and you have other tricks, it cannot be perfectly explained, but it works in practice. So at this moment, we do not have a very detailed, very fine explanation, but by building this bridge, you can think of this training. You can borrow tools from optimal control to help you to look at a different method in training the network. I'll give you one example. The Pontryagin maximum principle is well known in optimal control or in dynamic system, and the dual problem of it resembles a lot of, I think it's almost exactly the same as the neural ODEs that we have seen. And I have talked with people from dynamic system, and they look at a lot of things in deep learning, and they say, well, this is their comment, that in deep learning they do not use BP at all. They always solve ODEs to backpropagate, and they just told me a few days ago that a lot of things are actually reinvented, but it's already there in multiple control for decades. So I think there must be more things that we can borrow actually from each other. But back to your question, at this moment we do not have much more fine details to confirm this. Yeah.
Great, thank you. Let's thank the speaker again. The next speaker is Gail Weiss, and she's going to talk about extracting automata from recurrent neural networks using queries and counterexamples.
Hi. So this is a joint work with Yoav Goldberg and Eran Yahav. The name is kind of a mouthful, so what I really want you to understand is that we're going to be taking trained recurrent neural networks and extracting finite state machines from them, which is something a bit more interpretable. And because we all have different backgrounds, then really the first thing I'm going to do is just do a quick recap of what a finite state machine is, or what I call a finite state machine, or also a deterministic finite state machine, an automata, whatever you like. And it's simply something that can give a binary classification to finite input sequences over a given input alphabet. It has a set of states and a deterministic transition function between the states, so it reads input sequences token by token, each time doing a single deterministic transition for every token, and ultimately classifies a sequence according to the final state it reached, depending on whether it's accepting or rejecting. And our motivation is that we want to translate the recurrent neural networks into these finite state machines, because recurrent neural networks are kind of black boxes. We generally don't know any of the patterns that they're doing. We can only query them and give them simple sequences and see what they give. And finite state machines is something more interpretable. We can see the patterns and what they're doing if, for instance, there's a rejecting sync state somewhere or something like that. So it's more interesting. And then we can use that for knowledge extraction. For instance, if you have an NLP background and you have a great deal of data, which may be partial or even noisy, then you can train a recurrent neural network on it. We can generalize even given partial or noisy data, and then extract this far more interpretable model from the recurrent neural network. And it's also good for compression. If you imagine a finite state machine with only 4 or 5 or even 20 states, that's a lot more. That's a lot smaller than, say, all of the weights of a large neural network. And it's also faster to classify sequences because the transitions are simply pointer lookups as opposed to this sort of mathematical computation for every single token. And finally, and this is something that we weren't quite aiming for, but it's also something that happened, we can find flaws in the trained recurrent neural networks. So for instance, when we were trying to train an email network on something, we just wanted to create a nice email automaton to show you all, then during extraction, we actually ended up finding all these sequences that were misclassified by the network. So part of the extraction process returns all these sorts of interesting inputs to the network, and we found, for instance, that this network trained supposedly to recognize valid email addresses and with perfect train and test set accuracy, actually accepted the sequence 25.net, which you might recognize as almost being like an email, but missing an @ sign, or 5x.nem, which doesn't even have the right suffix. So this is also something that happened. And so we can assume that now we're convinced that we want to do this task. We want to extract our finite state machines from the recurrent nets. And now the question is how. So the first thing I just want to mention, an RNN is already kind of like a state machine because it has these hidden values and it keeps them and updates them with every input token it gets. So we can consider the concatenation of the hidden values as a sort of state. So we have here the states here are marked in green, in light green, and the RNN itself defines a deterministic transition function between these states. Every time we get an input, we take the input and the previous state, and we get the next state. The initial hidden values are like our initial state, which we also have in a finite state machine, and of course the final classification that we give according to the last output is the thing that defines the accepting or the rejecting states. I didn't mention this is of course for a binary classification RNN. Okay. The problem here is that the state space of the recurrent neural networks is continuous, so they could have infinite states, the amount of things that you can see. So mapping these states wouldn't be very informative. We wouldn't see anything very interesting, and so we want to maybe have something a little bit smaller. So our goal is actually to extract a concise or meaningful finite state machine from the trained recurrent neural networks. Now, we're not the first people to try and do this. So Omlin and Giles in 1996, for instance, suggested simply partitioning the state space of the recurrent neural networks by dividing every single dimension into equal intervals and treating these intervals as equivalent, and then simply mapping the states that are visited there in a sort of pruned BFS. So whenever you visit a partition that you have already seen, then you don't continue to explore it, and then you get a sort of finite state machine in this way. And there's been all kinds of works that mostly differ in the different ways that they create this partitioning. So just another example is Chechen et al. In 2003, which I think used k-means, but there's all kinds of things. And the problem with this partitioning is that we do it before we've started the extraction, and we get this kind of case where it's both too coarse and too fine at the same time. In one sense, it's too coarse because we don't necessarily divide the dimensions or generally the states where we should have divided them, so we might end up with two inequivalent states in the same partition. At the same time, it can be too fine. If we consider a recurrent neural network with 500 hidden values, and we simply split every single one of those values into two intervals, then we already have this huge amount of states that we can't handle or get any insight from. So we say we're not going to try and guess the partition in advance. Instead, we're going to start by not partitioning the state space at all. We're going to treat everything as exactly the same state, and we're going to refine our partitioning by some kind of iterative process, and every time we're going to split states only according to concrete examples, concrete proof. And we're going to get this concrete proof by using another algorithm for learning finite state machines, an exact learning algorithm called L-star, which was proposed by Dana Angluin in 1987, and it learns these finite state machines using membership queries and equivalence queries. Membership queries are where it gives you some kind of input sequence and it asks you to label, is this a positive or a negative sequence? And equivalence queries are where L-star actually proposes a finite state machine and says, is this your finite state machine? And I'm just going to do a quick run through. So we're going to learn, for instance, the language of all words that begin and end with the same letter over the alphabet A and B. So in the beginning, L-star just asks some simple questions, and we label them for L-star. So we accept all of these sequences. And then L-star proposes a finite state machine, for this case, just a finite state machine that accepts everything. And we tell L-star, no, this is wrong. You should reject the sequence BA. So L-star goes back and asks us some more questions. Oh, my God. Some more equivalence queries. I've gone way too slow, I'm afraid. So L-star does this iterative process and gets these better finite state machines. And we're going to use the equivalence queries to induce our partitioning. So I'm afraid I'm going to have to run ahead. So what we do is when we're doing equivalence queries, we're going to compare them to the abstraction of our finite state, of our recurrent neural network, which is induced by our current partitioning. And when they disagree, then if they disagree, then that means that there's a sequence that L-star and our abstraction don't agree on. And this means that one of them must disagree with the RNN. So we pass this one to the RNN, and if it disagrees with L-star, that's a counterexample. But otherwise, if it disagrees with our abstraction, then we find the root cause. For instance, two states, one rejecting, one accepting, that were mapped to the same partition, and we simply split that partition. And then we get this iteratively refined sort of setting. And of course, it's slightly more complicated, so I'll be really happy to explain it in our poster. That's the 19th poster. And I just want to quickly say our results. We got that when a network was trained well, then we extracted our finite state machines really well. So this is in a fifth of a second. We extracted the finite state machine I gave in the opening example. When a network had not trained onto what it wants, so for instance, we trained here on a context-free grammar. This isn't a regular language, the language of balanced parentheses, but it has these sort of regular approximations. And in fact, the network did not learn this correctly. And we saw in the counterexamples that were generated, and these are all the counterexamples that were generated, so they can be manually checked. We saw that some of them were misclassified by our network. So the counterexamples that are generated and returned to L-star during this iterative extraction are also very good adversarial inputs for our network. So they very quickly tell us networks that have not trained correctly, which is quite interesting. And of course, there's more results in the paper. So to summarize, we've got this novel extraction algorithm from RNNs to DFAs. It uses a dynamic abstraction and is the first application, at least that we know of exact learning to a trained RNN. It creates these concise and accurate automata from the trained RNNs, which is quite nice. And it quickly discovers adversarial inputs, which is also exciting. And I'll just be really happy to tell you more in poster number 19, because of course it's a lot more complicated than what I just explained. And I'll be really happy for you to try it out. So we've put a repository on GitHub. There's a notebook that you really just have to open and hit run all. We've even put it on Google Colab, so you don't even have to download anything or install anything. There's a link to the Google Colab from the repository. Try it out, ask me questions. I'd love everyone to use this. That's all, thanks.
Great. Any questions? So have you tried this on trained RNNs where you really didn't know what the structure was and what you would find by this?
So we haven't trained RNNs on things that we don't know in advance what they're going to be, but it has been a cute result sometimes to train an RNN on something that we input as a function, or for instance, balanced parentheses, and suddenly see how it actually looks as a finite state machine, because we didn't know in advance what these state machines would look like, just because we hadn't thought about it.
It could be very interesting to see what you got, for instance, with a humanoid control RNN, something like this, where you have a gate and you expect to see these definite sort of attractor states and such.
The sync
Appearing.
states, you mean? Oh, okay, so that's not something we've tried, but yeah, it's great. We're gonna want to expand this a lot further than where it is now.
Great, let's thank Gail again. Great. Our next speaker is Jiyuan Zhang, and she's going to talk about high-performance, zero-memory overhead direct convolutions. There we go.
Hi, I'm Juan. I'm from Carnegie Mellon University. My work is about the system-level performance optimizations for the computational kernels found in the deep neural networks. So this is work with my advisor, Franz Francelli, and co-worker Zimin No. So the structure of convolutional neural nets is going to be deeper and deeper. And the system memory is going to be more stringent in order to put all the growing size of weights and parameters. On the other hand, applications demand convolutional neural nets to be deployed on a variety of platforms, including those smaller and embedded devices, on which the computation and memory resource is even more a constraint. Given these trends, it is increasingly important that the computation of convolutions is efficient. There are 2 points in the efficient. So it needs to have minimal memory overhead and has fast computational performance. The conventional approach of computing convolution penalizes memory for optimal performance. For example, one of the widely used approach is stochastic convolution as a matrix-matrix multiplication problem. In this way, system developers can leverage the expert-optimized high-performance matrix library routines usually found in the BLAST libraries to get good performance for convolution problems. However, this incurs non-negligible overheads. So first of all, the image feature map the data needs to be packed and partially duplicated to form the matrix. As we can see, the resultant matrix ends up to be a lot bigger than the original image feature map tensor, which means system-wise you need more memory to store the temporary matrix. On top of that, the performance will also suffer because of the packing overheads. This graph shows the performance using matrix-based convolutions. So the dotted line is a baseline performance using the pure matrix-matrix multiplication. So it's a high-performance, expert-optimized matrix library. The blue bar is the matrix-based convolution. It's the actual performance that the convolution can achieve. The blue bar is always lower than the dotted line because of the packing overheads, and it introduced about 20 to 40% of the performance overheads. As a comparison, our customized direct convolution, which does not require transforming convolution into any other forms, gets 0 additional memory overhead and also higher performance. The performance is higher than the matrix-based convolution and also higher than the high-performance matrix library alone. So just a recap, and also the main point in our paper is, contrary to the conventional idea that convolution is a matrix-matrix multiplication problem, we are saying direct convolution is actually better and more efficient way to implement convolutions. It gets higher performance and 0 memory overheads. The reason is, first of all, direct convolution does not require reshaping the problem into any other forms, so it gets rid of all the memory and performance overheads associated with packing. Second of all, the computational performance of direct convolution can be higher than the high-performance matrix library. So hope you are convinced that direct convolution is better and more efficient. And now I think you may have the questions, like what's your technique of implementing a high-performance direct convolution that gets better performance, that can exceed the expert-optimized matrix-matrix multiplication library? Well, the high-level answer is it requires the understanding about your system architecture and the understanding about your application computations, and finding the proper mapping from the application to your system architecture in order to fully exploit the system's capacity. In our paper, we have in detail discussed all the techniques that is required to implement a high-performance direct convolution to achieve the system's theoretical peak performance. Because of time limit, I won't go into the technical details. But the main idea is we start with the analytical model of the system and step by step derive the optimizations that is required to sustain the system's theoretical peak performance. So those techniques including instruction scheduling to saturate computational pipeline, computation reordering, maximize data reuse, loop tiling blocking for memory hierarchies, and convolution-friendly data layout, and core-level parallelism. It's discussed in detail in the paper. You are welcome to read the paper or discuss offline with me. So just as a result, we get better performance so that the x-axis is all the convolution layers in AlexNet, VGG, and GoogleNet. The y-axis is the speed up. The higher, the better. The blue bar is the matrix, the high-performance matrix-based convolution. The green bar is the fast convolution method, which is the fastest one chosen between Winogrand and FFT convolutions. And the yellow bar is our direct convolution implementation, which gets about 30% to 400% better performance on all the networks. And this better performance is generalizable to a variety of architectures, including Intel, ARM, AMD, ARM. And we get better scalability. Scalability means as you increase the number of cores, the performance per core will not suffer, so that the total performance is linear related with the number of parallelism. So this is the performance of matrix-based convolutions. As you double the number of threads, the performance per core suffers. Or our direct convolution, as you double the number of cores, the performance will not suffer. And again, the better scalability is generalizable to different architectures and different networks. So just as a summary. So it's time to revisit the computation of convolutions, whereas a high-performance direct convolution gets zero memory overhead, while higher performance. And we show in our paper there is a systematic way for implementing high-performance convolutions that is generalizable to different CPU architectures, CNN networks, and both training and inference process. Thank you. And welcome to our poster.
Thank you. Are there any questions? So when you started working on this, are these the type of results that you hoped that you would see with this much sort of optimization of it, or is it more or less?
Yes, this is a type of results I expected to see based on the analytic models.
Okay.
Oh, okay.
There's a question here.
Yeah.
Thanks for the talk. It's really nice work. Do you have plans, or have you already released the source code or made it into like a plugin for any common framework like TensorFlow or anything like that?
We have not released the code, but we are open to these possibilities. And if you are a framework builder and if you are interested in this kind of work, I'm happy to talk to you.
All right, let's thank the speaker again. All right, we are continuing straight on to the next session, which is also on neural network architectures. And the first talk is being given by Noble Kennemer, and this is entitled ContextNet, Deep Learning for Star Galaxy Classification. Thanks.
Hello, everyone. Thank you for being here. My name is Noble Kennemer. I'm a PhD student at UC Irvine, and I'll be presenting ContextNet, Deep Learning for Star Galaxy Classification. This was done in collaboration with David Kirkby, Alex Eiler, and Javier Sanchez, all at UC Irvine. Okay, so just a quick overview of the talk. I'm going to talk about why do star galaxy classification, what it's used for, why it's important. I'm going to talk about what makes this problem hard. Basically, it comes down to atmospheric turbulence. And I'm going to talk about traditional approaches. So how have astronomers been solving this problem for decades? And then I'm going to talk about how could deep learning be applied to maybe do better at this problem. I'll give experimental results, compare it to the state of the art, and then I'll attempt to explain some of the predictions that our model is making. Okay, so star galaxy classification is a fundamental step in any astronomical survey. Specifically, we're targeting the Large Synoptic Survey Telescope, or LSST. LSST is probably one of the biggest ground-based surveys to happen in the next 20 years. It'll operate for about 10 years, starting in the early 2020s. It'll collect about 15 terabytes of data a night. And star galaxy classification is one of the fundamental steps in the astronomical processing pipeline. So where kind of we exist in the pipeline, so you expose a chip, which is just a single CCD, and you extract cutouts. Within each of those cutouts is a single object, and the goal is from those cutouts to predict, is the object in there a star or is it a galaxy? Okay, so what makes this hard? Well, in a perfect world, for astronomers without an atmosphere, it's a pretty simple problem. Stars are point sources, galaxies have some sort of spatial distribution, and so you could just measure the size of the object. If it's greater than 0, it's probably a galaxy. If it's around 0, it's a star. So this is basically the first column, the left-hand column on the figure. Stars, just a nice little point source. Galaxy has some sort of distribution. So what happens when you add in an atmosphere? Well, as light travels through the atmosphere, it's convolved with a response function. This is called a point spread function. Just for today's talk, it's a little more complicated than this, but you can think of it as just convolving the incoming light with a Gaussian. And then due to the turbulence of the atmosphere, the PSF varies with position, so from one place in the focal plane to another, and it also varies with time. So you can think of the spread of the Gaussian changing both spatially and temporally. And this is what is depicted on the right-hand column of the figure. And so when this occurs, the star, which originally occurred unconvolved as a nice point source, is now looking much more and more like a galaxy. And it's common, actually, that a star in one exposure could look bigger and more distorted than a galaxy in another exposure. Okay, so how have astronomers typically been solving this problem? As I stated, kind of the main signal for classification is the extendedness of the object. So unextended objects before convolution are stars. Extended objects are predicted to be galaxies. And so astronomers have developed several techniques for measuring extendedness, but they're all basically of the same flavor. What you want to do is fit two models to each object. You want to fit a model just of the point spread function, and you want to fit a model just of the galaxy. And why you want to do this is because since stars are point sisters, the two fits should actually be identical for the stars, but they should be different for galaxies. And so just to mention, both of these fits are selected from parameterized templates generally, so you usually are doing some sort of chi-square test to make these fits. And so from these two fits, you can measure what's called a magnitude. A magnitude is just the logarithmic brightness of an object. It's important to note that it's an inverse relationship, so the smaller the magnitude, the brighter the object, and the larger the magnitude, the dimmer the object. Okay, so we measure the magnitudes from the two models, so we get the magnitude for the PSF and the magnitude for the model, and then we can take their difference. And for stars, the difference should be nu 0, and for galaxies, the difference should be greater than 0. From this, we can make what are called size magnitude plots, which is what you're seeing. So basically, the size of each object in a chip is plotted on the y-axis with the magnitude on the x-axis. And then you make a classification cut, where everything below, you predict it to be a star, everything above, you predict it to be a galaxy. And this does really well for bright objects. The performance significantly degrades as you get into dimmer and dimmer regimes. And these dimmer objects are becoming increasingly important as astronomical surveys advance. So specifically, LSST will be seeing a huge population of dim objects that we've never seen before, and so it's important to get the classifications for them correct. And so convolutional networks have shown tremendous performance for these kinds of image classification tasks. So why not try it here? And when you leave the PSF fixed, both in, spatially and temporally, you get really good accuracy. If you let the PSF vary spatially, but you keep it constant temporally, you see the performance degrade some, but you can still get good accuracy. As soon as you let the PSF start changing from one exposure to the next, performance rapidly degrades to essentially random guessing. And even when you add more data, so when you double the training size, you're still stuck at random guessing. So what's happening here is a little more fundamental. It's that a single image of a star is actually not enough to make a definitive classification. You need the surrounding context of the other objects around it in order to make a definitive classification. And so you have this kind of local problem of wanting to model that one specific object, but you have this global problem of trying to model the entire PSF. And these two are tightly coupled. And so that is motivated the development of ContextNet, which is the model that I'm presenting now. So ContextNet is essentially 3 different neural networks. We use a lot of replication for this type of architecture. The first network is a local network, colored in blue, and it takes in a single cutout, and it outputs corresponding features to each object in the cutout, and it's replicated for as many times as there are objects in the chip. Those local features are then concatenated, and they are given as input into the global network, colored in yellow. And this is the first part of the model that actually sees the image in its entirety. And it was designed to provide the context necessary to make good predictions. We then have the prediction network, colored in red. This takes the concatenation of the global features, outputted from the global network, and the local feature for a specific object. And takes those two as inputs and makes a prediction. And this is again replicated for as many times as there are objects. And so there's replication happening both with the local network and with the prediction network. And both the global network and the prediction network are seeing the entire context of the image to make a prediction. And so, right, so some practical considerations. So our current implementation of the model, you have to define the number of cutouts beforehand, and they are fixed. But obviously, when you are collecting data from the sky, there's going to be a variable number of stars and galaxies in each image. So you have to be able to handle a variable number of inputs. So how we deal with this is a procedure that's similar to bagging. Basically, we define a minimum number of cutouts per exposure. So this is the minimum number that we know will be in the exposure. So for LSST, this is 1,000. If it's less than 1,000, then something probably went catastrophically wrong with the sensors. And then so we basically fill up without replacement a bunch of cutout sets. We do this multiple times. We predict on each of these sets, and we average all of the predictions. So this is how we're able to handle a variable number of objects in each exposure, which is a really important practical concern. And so another important thing to note is the architectures are pretty agnostic to each other. In our case, the local network was a convolutional network, and the global and prediction network were fully connected, but that's not at all mandatory. It's quite flexible. Okay, so how did we experiment? So as LSST is approaching, simulations are being done by a wide variety of groups in order to simulate every single aspect of the LSST pipeline. Basically, we have to simulate everything we expect to see and put it through the system, make sure everything looks good before we can turn the telescope on. And so we are making simulations using a high-precision image simulation package called GALSIM, which is widely used across astronomy to construct our simulations. We simulate 7,000 exposures, each containing around 12 to 2,200 objects, which is what you would expect for LSST. We train on 5,000, validate on 1,000, and test on 1,000. And so we compare with the current LSST classifier. So this is essentially the type of classifier that will be used for LSST. So how do we do? Well, we did better in precision and recall and accuracy than the current classifier, which is kind of the traditional approach that I mentioned earlier in the talk. And quite importantly, we did even better relatively on the dimmer objects. So as the objects, so what you're seeing in the figure on the right-hand side is accuracy bin by magnitude, and as magnitude increases, the objects become dimmer. And so both models degrade some in terms of performance with dimmer and dimmer objects, which is what you would expect, but ours degrades less. And so that's a really important practical concern also for LSST. And so whenever, interpretation's important for applying these types of deep models, and it's especially important for science. So one thing that we can take advantage of since we are using simulations is we have these essentially latent features which are used to build the simulation. So these are things like the size of each object, the magnitude, the eccentricity, the rotation angle. And these are things that the model never sees, but we know because we built the simulation. And so we can plot on the y-axis the probability that the model thinks it's a galaxy as a 1, 0 as a star. And we can try to look at these physically meaningful parameters and see if there's any kind of connections that we could use to try to interpret our results. So diving a little bit deeper, this is a specific plot, especially on the bottom, of size on the x-axis, and then again, probability of being a galaxy on the y-axis. And you see, which is quite physically intuitive, that as objects increase in size, they are more and more likely to be predicted as a galaxy. You also see some correlations with magnitude as well. But there's also kind of more to the story that's happening here. So you have some objects which are very similar in size and very similar in magnitude, but have very different predictions. So we can explain a little bit what's going on and try to provide some reassurance that the model's doing something reasonable, which it seems to be, but we can't explain the full story. And so with that, that concludes my talk. I'll be at poster number 36 if you want to discuss more about this project, or if you're interested in machine learning and astronomy in general. I do a lot of work in that area, so come talk to me about any of that. Thank you.
Thank you. Any questions? Please go to the microphone. So I was wondering two things. First, did you do any ablations on your model to see what the effect was of the local and the global parts?
What do you mean by ablations?
Just reducing the model, for instance, removing the skip connection that you have to the predictor,
No,
things
we did
like
not.
this.
Mhm.
Okay.
Yeah.
Anyone else? And no other comparisons except for to the LSST classifier?
Right. So all our simulations were done with respect to LSST. We did do some other comparisons using actually real data from space and correlating that with ground-based observations. We couldn't present that here because some of it's not fully public yet within the collaboration we're in. So yeah, we did, but we can't really present it. Yeah.
I see. Any other questions? All right, let's thank the speaker again.
Thank you.
All right, the next speaker is Mikołaj Binkowski, and he's going to present autoregressive convolutional neural networks for asynchronous time series.
Good afternoon. My name is Mikołaj Binkowski, and I'm a PhD student at Imperial College London. I'll talk about autoregressive convolutional neural networks for asynchronous time series. This is joint work with Gauthier Marty and Philippe Denat. So in many real-world problems related to time series, we have to deal with asynchronicity, which means that either the durations between consecutive observations in our time series are irregular, or if we deal with multivariate time series, the separate dimensions are not observed simultaneously. At the same time, usually time series models require both regularity of observations and simultaneous sampling. Also, continuous time models usually require simultaneous sampling. So people usually deal with these kind of problems at the preprocessing stage using some kind of interpolation method. However, no matter which one interpolation we would use, we would always end up either with more data points, or we'll lose some part of our information. If you look at this simple example, we have a snapshot of just 8 observations from some series, but they are concentrated at the beginning and at the end of this time frame. So if we use too low frequency, we pretty much lose every information that we have. On the other hand, if you would like to have a fixed frequency that keeps all of the information, we would have to have as many as over 12 times more data points. But the situation can get much worse. This is a snapshot of 1 day of trading at credit default swap market, and this is actually a data set that was motivation for our research. You can see here prices offered by many different market participants. As you can see, some of them are updated much more often than the others. And with this data set, if we would like to keep all of the information, we would have to have over 200 times more data points that we have initially. So our objectives were to propose an alternative representation for asynchronous series and find a good neural network architecture appropriate for such representation. So how can we deal with asynchronous data? Well, we decided to keep it as simple as possible. Assume that for now that we have just 2 series or 2 dimensions of one 2-dimensional series, we would represent each signal by its value and the one-hot indicator that will tell which dimension this signal comes from, and the duration from the previous observation. So first observation comes from the series X, so we have indicator X with positive value. Then the second observation comes from the other dimension, however, we also keep it in the same way, but with a different indicator, and so on. And at first we thought that recurrent neural networks should be appropriate for such representation. So for instance, LSTM has gating systems that, well, should be able to identify which observation is important for, makes an important signal for the prediction, and, well, this information might have been recorded and then used for the prediction. But surprisingly, it didn't work that well compared to simple autoregressive model. The same happened with one-dimensional convolutional networks. So we came up with an idea of, well, if the autoregressive model performs reasonably well, let's extend it and equip it with data-dependent weights that would identify the right important signals. So let's be a little bit more formal for a second. Assume that we have regressors of our multivariate series that comprise m past observations, and we would like to predict the next value of this time series at some target dimensions conditionally on such regressors. So our model proposes to use this formula where we have a weighted sum of adjusted regressors. This may look a little bit complicated right now, but we'll go through a scheme of this network, and I hope this will become very clear right in a moment. So we have our regressor and our input dimensions, and we pass all of this input in 2 copies to significance and offset network. These are both are modeled through convolutional neural networks, and we already required them to have as many output channels at the top layer as we have the target dimensions. And then the output of the offset network is added to the initial input to form adjusted regressors, while the output of the significance network is activated through softmax function and then used to weight these adjusted regressors. And in the end, we have our predictor that is autoregressive sum of these values. So you can think of offset network as a network that adjusts these simple predictors, while the significance network identifies the important signals. So we did a couple of experiments. Apart from the previously mentioned quotes data set, we also did evaluation on artificially generated synchronous and asynchronous series and electricity consumption data set available at UCI repository. And we compare it with a couple of benchmarks, such as vector autoregressive model, simple LSTM and multi-layer LSTM, ResNet, 1D convolutional neural network, and phased LSTM. And as you can see, the results for synchronous series, the ones on your left-hand side, well, our model was on par with the other networks. However, for all other data sets, it improved considerably, especially for electricity and quotes data set. So, well, in the other experience, we wanted to identify what were the reasons for its performance and actually which components of this model are important. So we found out firstly that the past observations are already pretty good predictors, and we just need to weight them, which means that the significance network was the one that needed more depth and therefore allow more nonlinearity. The offset network was also important, however, adding more layers didn't really help. In the other experiment, we wanted to find out what happens if we add some noise to the input and what happens to the mean squared error. And we found out that, well, if you look at these curves at the bottom, these are the curves produced for our model. And we see that our models were much more robust than the others, and especially on the test set, some of the other networks seem to have somehow skewed curves, which means that they overfitted the trained data set, even though we used many different techniques for that were supposed to overcome overfitting. That's it. Thank you very much for your attention. We'll be at poster 22 at Hall B tonight, and the code for our experiments is available online.
Great. Are there any questions? All right, let's thank the speaker again. Thank you.
Wait, just.
All right, the next speaker is Jonas Verman, and he's going to talk about hierarchical multi-label classification networks.
Yeah, well, hello everyone. My name is Jonas Verman, and I'm very glad to be here presenting our work, which is entitled Hierarchical Multi-Label Classification Networks. So let's get started talking about single-label classification, which is a very basic task. I'm pretty sure that everyone in this room knows it very well. So in this single-label classification task, the classifier must learn to predict between distinct classes. So for example, if a patient is healthy or sick, so it's very simple. In a multi-label classification problem, the classifier has to learn to classify between not necessarily distinct classes, but those classes may overlap. So in this case, an article might be classified as a sports category or economy, politics, and elections all together. So the classes are not disjoint classes. In a hierarchical classification problem, the class structure is actually organized in a hierarchical way. So the classifier has to learn this particular structure and classify the whole, an entire hierarchical path to predict the instance. So something like these, right? The classifier has to predict the entire hierarchical path. And the task we are interested in this work is what we call hierarchical multi-label classification. So in this task, the classifier has to predict not only the entire hierarchical path of the instances, but each instance may belong to several hierarchical paths. So something like this. We are proposing what we call hierarchical multi-label classification networks, or HMC networks, or HMCN. So our networks, they're based on three main components, architectural components, so local outputs, global outputs, and input reuse. The first one, the local outputs, this component is designed to learn local features for each hierarchical level in the hierarchical taxonomy. So the network has one output per hierarchical level. So if the hierarchical taxonomy has n levels, the network would be n local outputs. It has a global output, which maps deep features from all hierarchical levels, which aims to perform a global classification for the entire class hierarchy, not just local ones like the local outputs. And finally, the input reuse, which is a concatenation of the input features with all the latent features, global features, which helps both local information learning and local information learning. Okay, this is a diagram of our architecture. Let's start with the input feature X, which is processed by a fully connected layer, which generates our first global features, right? These global features are processed by what we call a transition matrix that generates some features to be classified in the first hierarchical level, right? And this process is repeated for the second hierarchical level, which receives as well the input features. And then we classify the classes for the second hierarchical level, and so on for the entire hierarchy. Finally, the global predictions use the latent features, the global latent features of the last iteration. And we concatenate all the local predictions, and the consensual prediction, final prediction, is actually a weighted sum between the global and the local predictions, and this trade-off between global and local is regulated by a beta hyperparameter. So one of our ideas was to try to formulate this global flow in a recurrent version. So we try to use layers with shared parameters, but it didn't work well. So we tried to adapt an LSTM version, which generating an hierarchical LSTM. So we can leverage the benefits of the LSTM, the residual connections in it, and we can continue performing local and global predictions as our previous approach. The problem is that it's hard to constrain the network to predict only consistent hierarchical paths. So to mitigate this problem, we introduce what we call hierarchical violation. So a hierarchical violation is when the score of child node is greater than its parent node. So we use this difference, the square of this difference as a penalization for this problem. The loss function, the overall loss function, is basically a sum between the local losses and global loss, altogether with our penalty of hierarchical violations. And we run experiments throughout 22 one datasets from 4 distinct domains. So let's get started with an ablation study. Here we analyze each individual architectural choices. So the first column shows the datasets, The second, a baseline, which is basically a deep network that uses ReLU, baseline, and residual connections. And then the input rules and local outputs, each component isolated to understand the importance of each choice. And the last column is our full architecture. So the full architecture performs very well when combining those options. So the effects of the hierarchical violation penalty, we can see that by using 0 of lambda or no using penalty at all, already gives us very nice results. And when we use slightly higher values for lambda, our results are consistently better, slightly better, but those results are very consistent. And when lambda is too high, actually the results are they are not so good. Okay, when comparing with state-of-the-art approaches, our two networks, they perform very well. The feed-forward version reaches almost perfect ranking in its performance, and the recurrent presents a very good ranking as well. So we outperform all the baselines in pretty much all data sets. Okay, and finally, we run some statistical analysis, and our first method, the feed-forward version, it is statistically significantly better than the strongest baseline. And that's it. Thank you very much for listening. And for more details, please visit us at the poster section.
Great, thank you. Any questions? It's a very quiet session. Yeah. Wondering if you have any other very different architectures that you've considered for this problem.
What do you mean by
beyond
very
the feed-forward one? Well, one might consider a recurrent neural network, for instance, that would continue to iterate over the categories and the,
yeah.
It should be interesting.
We did that, and this is our second approach that I just showed you.
Oh, okay.
Yeah.
Okay. All right, I guess that's it. Thank you very much.
Thank you.
There we go.
Okay, good. Great.
All right, great. The next paper is nonparametric variable importance using an augmented neural network with multitask learning, and it's going to be presented by both Jean Feng and Brian Williamson.
Great, thank you so much, and thank you all for being here today. My name is Brian, and this is Jean, and we're both going to tell you a little bit about our work this afternoon. So suppose that you're a physician and you're interested in taking medical tests and obtaining measurements in the order of their importance in predicting a patient outcome. So for example, you could be interested, and we'll continue this running example throughout, you could be interested in measuring both heart rate and blood sugar, and how do those things affect patient survival. So in order to actually address this problem, we need a couple of things. The first thing that we need is a definition of variable importance with minimal assumptions. So one way that you could think about measuring variable importance, sort of the classical way, is to use the ANOVA decomposition, which we know works really well in a linear model, but maybe doesn't work so well if the linear model doesn't hold. Maybe we're not quite so sure what actually is being measured. So this minimal assumption piece gets at what is the true variable importance regardless of the data generating mechanism. The second thing that we need is a method that estimates variable importance, and we want to do that reliably, right? So we want these, now instead of the stars, these dots indicate estimates, and so we want the variable importance estimates to be very close to the truth. And we also don't want to, we want to use a method that's flexible enough that doesn't incur estimation bias, right? So we need a flexible method to get at these true importances. And the third thing is that with different data sets and with different estimation procedures, there is some inherent uncertainty in the estimates that we obtain of this variable importance measure. So we want a way to quantify that and properly assess the uncertainty. For example, we might want to have confidence intervals. So in this example, on the left-hand side, I'm showing estimated variable importance with confidence intervals for the resulting estimates. And here, the data aren't really telling us anything about the actual true ranking between heart rate and blood sugar. Maybe we're not so sure which one is more important for predicting patient survival. Whereas on the right-hand side, these confidence intervals are pretty tight, indicating that the data do suggest that heart rate is more important than blood sugar, and so maybe that could inform physicians making a choice in how to allocate their resources. And the final thing for this variable importance measure and procedure is that we want our method to be computationally efficient, right? Because people aren't going to use the method if it takes a really long time to fit. So, this leads us to focus on neural networks in particular for doing the estimation, but we're going to have to use some tricks to get valid uncertainty estimates. So existing methods typically fail in one of two categories, or at least are unsatisfying in one of two categories. So neural networks, typically the variable importance measure is defined intrinsically to the neural network itself, so usually in terms of network parameters. So in that respect, it's sort of makes minimal assumptions about the true data generating mechanism, but the fact that this variable importance measure is defined intrinsically to the algorithm means that uncertainty assessment is extremely difficult, if not impossible. While obtaining these measures is very computationally efficient. So it misses on one, but hits on the other one. And current methods for non-parametric variable importance assessment, so now we're defining variable importance agnostic to the model that's being fit. There you get a valid estimate of uncertainty, but existing approaches, you have to fit many of these models to get importance for whatever subgroups you want. So they're not very computationally efficient. And our contribution is to do statistical inference on a non-parametric variable importance measure using an augmented neural network that gives us valid uncertainty assessments and also computational efficiency. So to make this formal, let's consider random variables x, which are our features. We have p features, and y is our outcome, distributed according to true data generating mechanism p0. So we're going to make no assumptions on what p0 is. It's allowed to be whatever it wants, but this is the truth that defines our random variables. We're interested in importance for x sub s, where s is any subset of the p features that we've measured. And the remaining features we're going to denote x minus s. So the importance then for x of xs relative to x minus s for predicting our outcome, we're defining in this way. It's the average squared difference between the full conditional mean, given all covariates, and the reduced conditional mean where I've removed the covariates that I'm interested in. And then I divide that by the variance of the outcome, so that this measure, psi 0s, lies between 0 and 1. And so how you can interpret this is first as the additional proportion of the variance in the outcome explained by including xs in our regression. And second, it can be readily seen that this is an extension, a non-parametric extension of the classical ANOVA decomposition or the classical R squared measure. So it's measuring the proportion of variance explained by xs. And to make this a little bit more concrete, let's go back to the heart rate and blood sugar example. So if we want to know the importance of heart rate, we can plot on the y-axis here the expected patient survival given only blood sugar information against blood sugar on the x-axis. And if we augment now with heart rate information, we can see in this plot that there's quite a lot of variability in the expected patient survival across levels of heart rate, indicating that perhaps heart rate is important for predicting patient survival because it tells us a lot about the differences in patient survival. Whereas if we play the same game with now blood sugar, so on the y-axis we have the expected patient survival given heart rate only against heart rate, and now we augment with blood sugar information, there's not as much variability, indicating that perhaps blood sugar is not very important in predicting patient survival.
Okay, so now we're going to talk about statistical inference of this non-parametric variable importance measure. And since we've defined it in terms of the population and it's agnostic to the estimation method we're actually going to use, then we can actually perform formal statistical inference. And the estimator we're going to be using is psi hat n. It's a very complicated expression. You don't have to read it in detail, but the point is you need the observed response, yi. You need an estimate of the full conditional mean. That's denoted with the hat. You need an estimate of the reduced conditional mean, y given x minus s, and the empirical variance. And the reason we like psi hat n is that it's asymptotically efficient, so it obtains the minimum asymptotic variance. And we can construct confidence intervals centered at this estimator. If you want gory details of how this whole calculation is done, come find us during the poster session. So now we're going to talk about how we're going to actually do this for multiple variable groups. And to do that, we would obviously need the conditional mean estimates, the reduced conditional mean estimates for every one of these variable groups. And we're going to denote our multiple variable groups with curly s. So the most straightforward thing to do is to estimate each of these conditional means separately. So if we were going to fit neural networks, we would fit a separate one for each of these conditional means. But you can obviously tell that this is very computationally expensive if we're interested in many variable groups. And this is the approach taken currently in the non-parametric variable importance literature. What we're proposing here is that we can do a slight modification to the neural network architecture to estimate all of these conditional means simultaneously. So we're going to call this the augmented neural network because it takes in the covariates x and it takes in a binary vector that indicates which conditional mean we're estimating. So a 1 in position I is going to indicate that xi does not appear on the right-hand side of the conditioning bar, so that's going to be some sort of reduced conditional mean, and a 0 means that it does. So for this example of 2 covariates, if you want the full conditional mean, you feed in all of x and you feed in 0 for the binary vector. If you want a reduced conditional mean, y given only x1, then you feed in x1, arbitrary value for x2, 0 for m1, and then 1 for m2. Since we want our augmented neural network to be able to estimate all these different conditional means, then we are going to train it by minimizing a multitask loss function. So that's the sum of the loss for estimating the full conditional mean and the loss for estimating the reduced conditional mean. And the two benefits we're getting from using this network is that computationally, the training time is about the same as the training time for a single network in the multiple network approach. And we also get a performance gain. So the fact that we used a single neural network to estimate all of these different conditional means implicitly regularizes them. So that translates into better finite sample performance. So to understand the performance of our estimator and also to check if the theory is going to match up with the empirical results, we ran a simulation study. So here are 6 covariates, and our response only depends on the first 4, so the rest are noise. And we're going to estimate the importance of one group, x1 and x2, and the other group, x3 and x4. So as the number of training observations increases, we see that the scaled bias converges to 0, and then the coverage of our confidence intervals converges to the nominal 95% value. And then finally, we applied our method to analyze 4,000 patient records from the ICU, and these records have medical test measurements that come from the first 48 hours of their stay. And our goal here is to understand the importance of these medical tests for predicting in-hospital mortality. So on the y-axis, we have ranked these are variable groups by medical test, and we've ranked them in order of importance. And at the very top, we have the Glasgow-Coma score. And so this kind of makes sense because it's a scoring system that measures patient consciousness. So it has very basic, it's measuring basic abilities like can you move your eyes, can you respond verbally, do you have motor control? And it's the highest scoring item in many ICU scoring systems. On the other hand, at the very bottom, we have temperature and urine output, and those confidence intervals are covering 0. So that suggests that these two measurements are not giving us much more information compared to the other medical tests. And this is kind of interesting because different ICU scoring systems, well, depending on which ICU scoring system you use, temperature and urine might not actually be in that risk assessment score. So our results here seem to suggest that it might be okay to exclude those two measurements. So using these results, we can kind of guide how you're going to prioritize these medical tests for predicting in-hospital mortality. But obviously, if you want to actually bring this into medical practice, we would want to test it, validate it in the clinic. So to conclude, we've proposed estimating a non-parametric variable importance measure, and because it's defined on the population and is independent of the estimation method you've used, it enables us to do formal statistical inference. So we have estimates and confidence intervals. And then we're using an augmented neural network that allows us to estimate all of these values computationally efficiently and also gives us improved finite sample performance. So we're going to be poster 139 tonight, so come find us.
Thank you. Any questions?
Very interesting work. How much of this is model dependent? Like if you change the network, how much the ranking change?
Well, we use this architecture for mostly trying out, or we vary the number of nodes in this architecture and didn't change the ranking much. We've also, in the poster, you can see that we've fit multiple networks, and the ranking is roughly the same, though like things will shift around a bit. Yeah, but I think we have tried like completely different architectures, and the reason we chose this one in particular is because if you had infinite, or if you grew the network large enough by the universal approximation theorem, it will approximate all your conditional means correctly.
And all you need to do is get a good enough estimate of those conditional means, so the architecture can change as long as you're doing a good enough job.
And you could use any estimator at this point.
Yes.
Yeah.
Thanks.
Great. Anyone else? All right, thank you. So the next speaker is Suraj Srinivas, and he's going to talk about knowledge transfer with Jacobian matching.
Hi everyone, I'm Suraj Srinivas, and I'll be presenting our work on knowledge transfer with Jacobian matching. And this is joint work with my supervisor, Francois Fleuret, and we are from EDAP Research Institute and EPFL in Switzerland. So let's consider the neural network A, shown in the top right of the figure. So we can rewrite this neural network in several equivalent ways. So we can either permute the neurons in the layer, or we can add an identity layer, or we can add a redundant neuron. So all of these are different parameterizations of the same underlying function. So we knew this already. But what this tells us is that if we really want to describe the underlying function, then we need tools or quantities that are parameterization invariant. So tools that don't change when we do all these operations. So this is especially important when we do regularization, for instance, because we're only interested in restricting the space of functions, and we don't really care about the underlying parameterization. So we need to use parameterization invariant tools for regularization. So in this talk, we'll consider one such tool, which is the input Jacobian, which is essentially the vector of partial derivatives with respect to of the outputs with respect to the input. In this case, y is a scalar, but in general, if the output is k-dimensional, then the Jacobian is d cross k if the input has d dimensions. The important property of the Jacobian is that it is invariant to parameterization of the function. This arises simply as a consequence of the chain rule. But a more interesting property is that if we consider ReLU nets without bias, then the output can be simply written as the dot product of the Jacobian and the input. This means that the Jacobian actually captures all the information or the computation that is performed by the neural network. This is quite helpful. But this doesn't hold true when we consider non-ReLU neural nets or ReLU neural nets with bias. So we shall apply the Jacobian to the problem of knowledge transfer. So let's consider that we have a student network and we want to train it on a data set A, but then we're not happy with the performance that the student achieves on data set A. So we can strive to improve its performance by providing hints from a teacher network, which is possibly trained on a slightly different data set B. So if the data sets A and B are the same, then this task is called distillation in literature. Otherwise, in general, it's a form of transfer learning. Now, if the architectures of both the teacher and the student are the same, in this case, then we can simply copy the weights. It's easy to see this. For the case of distillation, it's very trivial. But for the case of transfer learning, this is something similar to fine-tuning, where we initialize the weights of the student with that of the teacher. But in the general case, where the teacher and student have different architectures, we need to use hints that are parameterization invariant. We cannot use weights because they are the parameterization, essentially. So it's natural to use the Jacobian in this context, but previous works have also used the Jacobian. But the difference is that we also motivate the choice of the loss function to use for Jacobians, and we also connect with previous distillation methods. So one of our contributions here is to connect Jacobian matching with input noise. So let's consider a teacher curve shown in blue on the top row of the figure, and let's consider that we have a limited number of data points available with us. As a result, this problem is underdetermined. So this means that several students can fit the data points that are given to us. So to overcome this problem, we have two equivalent solutions. The first one is to just match with input noise. And the second one is to match the slopes of the teacher and the student during matching. So from the diagram, it's clear that these two are equivalent. But it turns out it's also equivalent in a more general case, where if you have a teacher network T and a student network S, and you match their outputs with input noise, then you can decompose them into two loss terms, one where you just match the outputs and the other where you match the Jacobians. Notice here that the term on the left is actually interactable to compute because of the expectation, especially when the inputs are high dimensional. But the terms on the right are completely tractable. And this approximation is an equality for the case of ReLU networks when your noise is small. Okay, so this is for, that was for knowledge transfer, but what happens when we don't have a teacher network? So in that case, we can strive to make our network robust to input noise. In this case, we end up with a regularization term where we minimize the norm of the Jacobian. But this is not a new idea. This was proposed by Bishop in 1995 in the paper Training with Noise is Equivalent to Tikhonov Regularization, where the observation was that for linear models, the Jacobian is exactly equal to the weight matrix. So Jacobian norm regularization is exactly the same as L2 weight decay. But this is not true for neural networks in general. L2 weight decay and Jacobian norm regularization are not the same. So this tells us that if we really want to make our neural networks robust to input noise, then we must be using the Jacobian norm regularization and not something else like weight decay. So let's apply these techniques to the problem of transfer learning. In this case, we consider this very interesting technique called learning without forgetting. We'll call it as LWF in the talk. So this is a transfer learning method where the idea is that we want to train the student on a target data set shown in green. And here the student has two objectives. The first objective is to match the ground truth labels of the target data set, which is its primary objective. And then the secondary objective is to mimic a teacher's response on the target data set. But the important point here is that the teacher is not trained on the target data set. So the teacher is a generic pre-trained network. Let's say it's trained on ImageNet, which serves as a source data set, but it has never seen the target data set before. Now the hope here is that the learning of the teacher is generic enough so that the training on ImageNet carries over to that of the target data set. But then we are not really sure. So this is fundamentally puzzling. We don't know why this kind of method should work, even though it has good empirical success. The teacher can provide noisy outputs here, and it may not really help transfer learning. So when does this method really work? So to answer these questions, we have a few theoretical results. This tells us that this method LWF works when you have a teacher network with small Lipschitz constants, which means that it's smooth, and when a notion of distance between the source and target datasets is small. Here the source dataset refers to ImageNet, and the target dataset is what we want to train the student on. This just means that this method works when we are using this method on a target dataset which is not too different from ImageNet. And that makes intuitive sense. If we try to use the ImageNet representations for something not related to images or the geometry of images at all, then we don't expect transfer learning to help, and that is what this result tells us. Of course, this is in addition to the constraint that the teacher must perform well on ImageNet. And the other result is that improving distillation by Jacobian matching also improves LWF as a result. So for the exact statements, please refer to the paper. These are just simplified versions of them. So, but one thing that is crucial is that we use the equivalence between Jacobian matching and training with noise for the proof, and that is a critical component of it. So coming to the transfer learning results, we see that LWF with Jacobians actually performs better than LWF, and also when we consider variant of LWF with attention. But what we observe is that we are not able to be better than a fine-tuning oracle, which has a constraint that the teacher and the student have the same architecture. In this case, the fine-tuning works better, but in the more generic case, where the teacher and student have different architectures, we must use either LWF or the variants with Jacobians. So this means that if we don't have a pre-trained net of the architecture we want sitting out there, then these are the kinds of methods that we must be using. Thank you for listening. To summarize, we have used Jacobians for, there are parameterization, invariant quantity used for distillation, transfer learning, and robustness. You can see the other results in the paper. And this viewpoint of data augmentation motivates its use in low data settings. So if you want to hear more about this work, please visit us at poster number 204. Thank you.
Thank you. Are there any questions? So did you look at, I know there are a lot of different data set pairings that are used, like in the LWF paper. Did you also look at, do you also get improved performance on those other transfers?
We did not look at any other data set pairs because our focus was on trying to understand the various scenarios in which Jacobian matching could be used in addition to transfer learning, because that's just one of the tasks. So yeah, because of space, we did not consider the other data sets, but that would be interesting to try.
Okay. And it seems like this could be a useful tool for regularization as well, rather than just knowledge transfer.
Yes. We observe that we get robustness to input noise when we use this, so it's indeed helpful.
All right, thanks. Let's thank the speaker one more time. And this concludes the session. Thank you.